Good afternoon, everyone. My name is Han-Chen Wu. Thank you for coming to my presentation. I'm so sorry that we could not present the paper at the conference in person due to visa issues. Today, I'm going to present our work on compiling SIMT programs on multi- and many-core processors with vector units. Many-core processors and coprocessors have played a significant role in high-performance computing due to their high performance and power efficiency. This simple picture shows a many-core architecture where each CPU core has its own cache and memory, and they are interconnected by certain networks. Many-core architecture shows multiple instruction, multiple data parallelism, where each CPU core performs a different task. To enhance the computing power, each CPU core can be paired with a vector processing unit. Vector lanes of the same VPU perform same instruction on different data, exhibiting single instruction multiple data parallelism. We see here a scalar CPU is paired with a VPU. The CPU core still issues scalar instructions as normal, but it can also issue vector instructions to VPU now. A vector instruction takes several vector variables as input and return a vector value as output. It can also optionally take a masked variable, which can mask out inactive vector lanes by setting its corresponding bits to 0. Vector lanes within the same VPU execute in lockstep. Intel has launched several commodity multi- and many-core architectures with 512-bit vector units, providing massive computing power. Examples are Xeon Phi coprocessors, Xeon Phi processors, and Skylake processors. We call them hybrid architectures in our design, since such architecture exposes both MIMD and SIMD parallelism. To get the maximum performance, programs running on hybrid architectures require the use of both CPU cores and their vector units. To explore the CPU cores, we need to use MIMD programming models such as OpenMP and pthreads API. To utilize the vector units, we either use compiler-based pragma directive or perform manual vectorization with vector intrinsic functions. However, such a programming model is tedious and error-prone. Hence, there has been an increasing interest in supporting single instruction multiple threads programming tools on hybrid architectures so that we can program every vector lane as program a scalar CPU core, allowing the simultaneous use of all CPU cores and their vector units. To this end, in our work, we first propose compiler techniques to deploy programs written using a SIMT-styled CUDA-C on hybrid architectures with 512 vector units. We then evaluate the proposed code transformations on different platforms and identify the main performance bottlenecks. We also provide insights on how to support efficient SIMT model on hybrid architectures. Here is our supported SIMT-styled programming language, a subset of CUDA-C. All of our benchmarks and applications are written with this CUDA subset, then transformed into code for the hybrid architectures considered. We support 32-bit integer and float data, various arithmetic operations. We support shared memory and block-level synchronization. The first design question is the mapping of the threads of a CUDA kernel onto hybrid architectures. On GPU, CUDA threads are grouped into warps and mapped onto scalar cores on streaming multiprocessor. CUDA threads are also partitioned into CUDA thread blocks, and each CUDA thread block consists of one or more warps. As shown here, our compiler transformations map a CUDA thread onto a VPU lane and a CUDA thread block onto one or more x86 hardware threads. Since the hybrid architectures considered here have 512-bit VPUs and we support 32-bit variables, our implementation assumes VPUs with 16 vector lanes. Therefore, given a CUDA warp that consists of 32 threads, each CUDA warp is then mapped onto 2 hardware threads on hybrid architecture. As a consequence, each CUDA thread block may be mapped onto multiple hardware threads. For a SIMT model such as CUDA, control flow statements are executed by each CUDA thread, and the control flow is maintained at the CUDA thread level. On hybrid architecture, the control flow is maintained by the threads running on the x86 cores. Thus, supporting SIMT model on vector units requires handling the case when different VPU lanes follow different execution flows. To support this functionality, we associate a mask variable to each block scope and issue all the vector instructions in the block scope using that mask. Here we show an example with loops. We discussed the transformation of while loop and for loop together because they can be both expressed in the form shown above here. The loop condition is evaluated at each iteration of the loop to determine if the loop must be terminated. The condition is updated during the execution of the loop body. Here below we show the transformed code. The while loop body is identified as a program block. Therefore, we assign a mask variable and while to the scope of the block. A 0 bit in the mask and while indicates the corresponding vector lane has exited this while loop. At high level, when 16 repeat lanes execute a loop, the execution cannot leave the loop until all lanes have completed the loop themselves. The condition evaluate statement here updates the mask variable and while, and the loop terminates only when all the bits in the mask and while are set to 0, indicating that all vector lanes have completed the loop execution. All vector instruction inside the while loop is issued with the mask and while. This guarantees SIMT execution on vector lanes. And we can perform similar transformation for if-else control statements and function calls. To summarize our design, our tool chain consists of two modules, a kernel launch module and a kernel body vectorization module. Given a CUDA kernel, the kernel launch module is responsible for threads creation and grouping, the initialization of shared memory, synchronization barriers, the initial mask variable, and the vector lane IDs. This module is the same for every kernel except that it takes a different set of parameters at the kernel invocation time, such as kernel configuration and input parameters. Second, the kernel body vectorization module is enabled by a source-to-source translator. The transformation starts within the main kernel body. It first replaces scalar operations with corresponding vector intrinsic functions, then creates a mask for each child program block. Then it will do the same translation recursively for each child block. This table summarizes the platforms used in our evaluation: a Xeon Phi coprocessor, a Xeon Phi processor, a Xeon Skylake processor, and for comparing purpose, 3 NVIDIA GPUs with the following architectures: Fermi, Maxwell, and Pascal. We use these abbreviations in the charts. If it starts with a G, it indicates a GPU device, and an H indicates an Intel hybrid architecture. We have designed a set of micro benchmarks to evaluate the overheads and performance limiting factors of the proposed implementation. Specifically, we evaluate the performance of kernel launch, irregular memory accesses, control divergence, thread block synchronization, and shared memory accesses. This slide shows the result of kernel launch overhead. X-axis shows how many CUDA warps are configured. Y-axis shows the kernel launch time in milliseconds. For the Xeon Phi coprocessor, we test both the offload and the native execution model. As can be seen, on all GPUs, the kernel launch overhead is very low, about 0.05 milliseconds, independent of the degree of multithreading. This is expected since GPUs do not run an operating system. On the other hand, on hybrid architectures, this overhead is substantial and increases almost linearly with the number of p-threads spawned. The Xeon Phi coprocessor reports the highest overhead in offload model and the second highest in native model. On the Xeon Phi processor, the overhead is lower but still significant. The Skylake processor reports an average overhead of 0.13 milliseconds per p-thread creation. Here we show the pseudocode of the micro benchmark of the irregular memory accesses. On hybrid architectures, when a VPU accesses non-contiguous memory locations, they trigger get and scatter vector instructions. We see that each SIMT thread reads from input array and writes to output array iteratively. The total number of reads or writes is equal to the input array size. Parameter random degree controls the irregularity of the memory accesses. When random degree is equal to 0, memory accesses are regular. The larger random degree is, the more irregular the memory accesses are. In the experiments, we first test read and write performance. We then remove the write operation at the line 4 and measure the read performance alone. In both cases, we measure the performance when a single warp is run and when all the cores are fully utilized. Here, x-axis shows the random degree and the y-axis shows the execution time in milliseconds. On a single CUDA warp, Xeon Phi and Skylake processors report better read and write performance than GPU, independent of the value of the random degree parameter. The Xeon Phi coprocessor reports faster reads than GPU only when the memory accesses are fairly regular. Next, when all the processing cores are used, the Xeon Phi and Skylake processors report faster read and write accesses than Fermi GPUs, but slower accesses than Maxwell and Pascal GPUs. The Xeon Phi coprocessor reports the worst read and write performance. If we remove the write operation and test the read-only accesses, the trends are similar. Now we show the pseudocode of the control divergence microbenchmark. Control divergence occurs when SIMT threads executing in lockstep take different execution paths. As can be seen, this microbenchmark executes a control flow block with up to D divergent branches, where D can vary from 1 to the warp size. To exclude the potential influence of the memory system, this microbenchmark does not issue memory operations. Here's the result. We can see that on all the platforms considered, the running time increases almost linearly with the degree of divergence D. The cost of control flow divergence on hybrid architecture is comparable to that on GPUs. Here, our thread block synchronization microbenchmark invokes the sync-thread primitive iteratively. In our experiments, we set number of iteration to 1 million on a single thread block launch and increase the block size gradually. In the result chart, x-axis shows the thread block size, and y-axis shows the execution time in logarithmic scale. On GPU, where thread block synchronization is supported in hardware, the overhead is low and independent of the thread block size. On the other hand, on hybrid architectures, the synchronization overhead grows significantly as the block size increases. This is because synchronization is implemented using barrier variables stored in memory. For large block size, hardware threads mapped to the same CUDA thread block can run on multiple physical cores, causing synchronization to trigger memory traffic across the private L2 caches. We see that the synchronization cost is significantly higher on Xeon Phi coprocessors than on other hybrid architectures. This is due to that Xeon Phi coprocessors have a bidirectional ring bus connecting the L2 caches, which is slow in performance. I skipped the shared memory microbenchmark here due to time constraint. Also, it's similar to the results of the irregular memory accesses benchmark. This table summarized real-world applications used in our evaluation. In all cases, we indicate whether the application uses shared memory in SM column and whether it performs iterative kernel invocations in ITER column. Here we show the results on hybrid architectures and compare it with the best GPU result on Pascal GPU. Applications with iterative kernel invocations can hardly benefit from running on hybrid architectures. Examples are BFS, Hotspot, Pathfinder, and Gaussian elimination. This is due to the kernel launch overhead. We found out that the running time of these applications is dominated by the kernel launch time. For Hotspot, although it performs only 4 kernel invocations with the given input, the Pascal GPU outperforms the Intel platforms also on this application. On hybrid architectures, Hotspot, due to its large thread block configuration, suffers from thread block synchronization overhead. KNN reports better performance on the Pascal GPU than on the Intel platforms considered, mainly due to its regular memory access patterns. On the other hand, nearest neighbor reports the best performance on hybrid architecture, the Xeon Phi processor. This is due to the following reasons. First, it uses neither shared memory nor thread block synchronization. Second, it is implemented as a recursive call that traverses an irregular tree. Recursive calls on hybrid architectures are more memory-friendly than on GPUs. Finally, we can observe that despite using shared memory, Levingston reports the best performance on hybrid architecture, the Xeon Phi processor. This is due to several reasons. First, it has a long-running kernel that amortizes the kernel launch overhead. Second, its shared memory is cached in a single L2 cache, allowing reduced memory traffic on L2 cache. Third, no thread block synchronization is needed since the thread block size of the kernel is 16. Last, the memory access patterns of its kernel meet the alignment requirement, which allows the use of fast load and store vector instructions rather than the slow gather and scatter instructions. To conclude, in this work, we have proposed compiler techniques to transform programs written in a subset of CUDA-C into codes that use the pthread library and vector intrinsics to run on hybrid architectures. We have compared the performance of the original CUDA codes on GPU with that of the transformed codes on several Intel platforms. Our analysis points out several performance-limiting factors that result in poor performance of existing CUDA applications on hybrid architectures, such as iterative kernel launch, thread block synchronization, and use of shared memory on large thread block configurations. Even so, Intel 5 processors outperform Pascal GPUs on certain CUDA codes written for GPU devices. And we have some future work planned. For example, the PGI compiler has supported AVX 512 vector instructions in their latest release. We should compare with their results on Intel 5 processor and Skylake processor. And in case of iterative kernel invocations, we try to use persistent threads to reduce kernel launch overhead. However, since we need global synchronization between each kernel invocations, the use of persistent threads will not benefit too much unless we could find fast synchronization implementations. In the end, thank you all for coming to the presentation, and I'm sorry again for not being there. Feel free to contact us for presentation slides and the YouTube link. Thank you. Bye-bye.